Alrighty, good morning, everybody. This is our heat transfer project for ME573. Today we're going to be talking about how me and my team tackled the thermal management system design for a Cislunar satellite. So over here you can see the mission context and requirements. It was specified for our project that we are designing a satellite and cooling systems based on a cislunar orbit. This is a low Earth orbit, and the specific orbit that we have selected is the ELM2 halo orbit. It sits approximately around 62 to 65,000 kilometers above Earth's surface. Along with that, the project states that onboard electronics electronics on board of the satellite core generate approximately 5.5 kilowatts of thermal energy. And with that known, our goal is to design a thermal management system that will maintain a core temperature between negative 10 degrees Celsius and 40 degrees Celsius. It's also required that we complete this using only heat rejection via radiation to space. So our project design goals are listed here. Obviously the main goal that our team is focused on is maintaining temperatures. As we get further into this presentation, we are going to lay out the two extreme cases for which we have based our design. The halo orbit that we have selected includes two extreme cases. It is a 7-day orbit with approximately 165 hours of sun exposure time and 3 hours of potential eclipse time. Using these two metrics, we proceed to control the core temperature for both of those extreme conditions. We're going to refer to those as the hot and the cold case. Furthermore, we are going to reject internal and environment coupled heat to deep space. To achieve this, our team has decided to use a closed loop ammonia based cycle. This will be very nice because that includes no mass loss and lends itself to long life missions. We aim to minimize the power draw as well as the system design complexity, and then we look to maintain a continuous electrical power supply to the satellite for all extreme cases. So my job when we were starting this project was to size our power system. Our team has decided to go with solar panels coupled with rechargeable batteries to provide all the necessary power that will be drawn for the life of this mission. To do this, I basically started by picking the batteries. The size of our batteries is going to be based on the worst case scenario where our satellite is under full eclipse for approximately 3 hours. To get this load and the nameplate rating for the battery, I took the time for the eclipse multiplied by the designed electrical load. And as you can see here, the designed electrical load includes about a 20% margin over our baseline energy generation. Performing this calculation, I calculated that we need approximately a 20 kilowatt hour battery. And this number is going to be super important when we move on to designing the solar array. The approach that I took for picking the solar array area was we need the solar panels to be able to recharge the battery over the total sun exposure time. So if we use 20 kilowatt hours during the eclipse, we need to be able to recharge that 20 kilowatt hours via the solar panels while we are exposed to the sun. Sun exposure time for our selected orbit is approximately 165 hours. And factoring in the incident load from the sun, the efficiency factors, some packing factors, some niche things that are typical in spacecraft and satellite solar panel design. We calculated an approximate solar array load of 7 kilowatts. Using this number, we got that we will have a solar array consisting of two panels that are going to equal a total of about 22.5 square meters of solar panel area. Now I will pass it off to Carson Johnson to discuss the core model and geometry.
Thank you for the introduction, Aiden. So yeah, as Aiden said, we're now going to get into the core geometry. So for this project, we're assuming the core of the satellite to just be a cylinder. The length of the cylinder will be 10 meters, the diameter will be 4. So calculating the surface area of the core, you end up getting a total external surface area of approximately 151 meters squared. So as Aiden mentioned, we will have electronics generating heat within the core itself. And we're going to also assume that all of the heat generated by the electronics will end up at this copper heat sink that will be approximately 30 degrees Celsius. And this is a good linking point from the heat coming from the electronics to the fluid that will then allow the heat to be removed from the system. So for the geometry of the core, most of our core will be covered with MLI, which is multi-layer insulation. The reason for this is that especially on the cold side, when the sun is being blocked by the earth, you have very little solar radiation, you have very little reflection from the earth of solar radiation, and the core can reach very, very low temperatures. So the insulation prevents the core from reaching freezing temperatures, which would freeze up our electronics and cause many other issues as well. So we will have the multi-layer insulation covering a lot of the core, but certain areas will be coated with Z93, which is white paint, and this helps with thermal control, and this is more for the hot side of it. So when the core is exposed to a lot of radiation, you don't want all of that radiation coming in, or else therefore the core would reach temperatures that would be too high, and it could melt the electronics or cause other issues as well. So this allows very little absorption of solar radiation. So now we're going to discuss the hot case that I mentioned earlier. So calculating the solar load, which is the radiation from the sun to the satellite, we use this equation directly below it. You take the area, which this is the projected area of the core. So we are assuming this to be almost like a plane wall, just taking the diameter times the length, because that is all the part of the core that the sun actually sees. So you take that projected area of the core, you multiply by the absorption of the white paint that will be exposed to the sun, and then you multiply that by the radiation from the sun, which is about 1360 watts per meter squared. So that's from the direct solar load. You also have the Earth albedo contribution. Now this is the radiation that is reflected from the sun by the Earth. And this is a really similar case of how you solve for this. Take the absorption, you multiply by a view factor, and then we also did 30% of the radiation from the sun, which ends up giving you 410 watts per meter squared. This is a safe assumption, and it's consistent with current ways and current calculations that they use for designing satellites currently. So then the last part of radiation that the core is exposed to is the infrared contribution from the Earth. The Earth itself emits radiation that will also cause the core to heat up. And this is a similar equation. You just take the emission times the radiation from the Earth times the view factor times the area of the satellite itself. So the total radiation on the core from albedo, solar, and Earth's radiation is approximately 20 kilowatts, and the total absorbed by radiators, panels, and core is 53.8 kilowatts. So the solar panel part it has more flexibility in terms of temperature control. It can reach higher temperatures and reach lower temperatures. For the project requirements, all we were required to do is keep the core within negative 10 degrees Celsius and 40 degrees Celsius. So we use the radiation that this is experiencing to determine the temperature of the core on the cold side of the cold side as well as the hot side. And now I'll introduce our very own Logan Cutting.
All right, thank you, Carson. So now we're going to talk through the heat transport loop a little bit. We decided to go with the working fluid of ammonia. We chose this because it is typically the industry standard for spacecraft due to its high specific heat of 4841 joules per kilogram Kelvin, and then its wide range of operating temperature. Its freezing point is negative 77 degrees Celsius, so that'll very well cover the negative 10 that was in the outline. So now just a bit of design input. Our delta T is going to be the uniform temperature fluctuation of 5 Kelvin, so we can keep the core cool. And then we went with a pipe diameter of 0.02 meters, and we sized it small so that we can get the fluid flowing at a good rate, not too slow or too fast. Then we went on to calculate the mass flow rate. We did this by dividing the core heat by the delta T times Cp, and we got a value of 0.3 kilograms per second. Next, we did the velocity with this, and this was calculated by taking the mass flow rate divided by density times the cross-sectional area of that pipe that I mentioned earlier. We got this value to be 1.5 meters per second. And then onto the pump power. Since the pressure drops for fluid flow, or since the pressure drops from fluid flow were negligible, the work of the pump for the sustained flow was 4 times the power, so we did 4 times mass flow rate times the velocity squared to get 1.5 watts. And then we are also going to add a thermal bypass valve. This will be useful for when we're in the eclipse. The valve will actually shut off so we can keep the heat inside of our system. And then once we get to that hot case when we're between the sun and the earth, that will actually open up, allowing for fluid to flow through, and then we can get the heat out of the core. And here's the graphic as well. Now onto the radiator sizing. So the radiator coating for this, we went with Z93 white paint. Again, this is kind of like a standard for spacecrafts. And this paint is good because it has a high emissivity of 0.9, which dumps the heat faster, and then an absorbity of 0.2, which absorbs a little heat from the sun. So now onto the surface temperature of the radiator. We decided it would be good to make it 17 degrees Celsius. The fluid flowing through that heat loop is going to be 25 degrees Celsius, and we want the radiator to be less than that, so we draw heat from that loop out of our system and then radiate it into space. So that was the reasoning behind that. And then onto the rejected load, which is the total heat that we must get rid of from the core and the pump. So just add those together. We got 5501 watts, which makes sense because the pump power was low. And then onto the radiator area, we did the rejected heat divided by heat out minus heat in. We got 18.5 meters squared for this. And then to calculate the absorbed load, which is the unwanted heat the radiator picks up from Earth while trying to cool, we did heat in times the radiator area, which we got 1185 watts. All right, so now kind of like the design of this radiator, we implemented it as 2 deployable panels, each sized at 9.25 meters squared, so that's just the area divided by 2. Both of them will kind of come out. It makes for more of a sleek design, and we thought this would be something cool to add. And then the panels are also oriented to avoid direct solar radiation and then minimize the heat from Earth. We're pointing them away from the sun when we're between the sun and the Earth so that we don't absorb that amount of heat. All right, so now Carson's going to come back up here and talk about the cold case.
So now we're going to discuss the cold case in a little bit greater detail. After discussing how the radiator would actually remove heat from the system, that you now have the opposite case where the solar radiation is being blocked by the Earth. And as I mentioned earlier, this is different because now you got to worry about the core freezing up, and that's where the multi-layer insulation comes in. So yeah, as I mentioned, we're assuming no direct solar and radiation, as well as negligible albedo in the eclipse, which, as Aiden mentioned earlier in our presentation, the eclipse will be about 3 hours, and we are assuming absolute worst case scenario. This is worst case scenario, provides us some safety margin, and prevents the core from ever freezing up in normal operations. We're also using the Earth infrared flux of 220 watts per meter squared, which is consistent with current data and what it averages out to be on average. So in the cold case, the entire load, external load on the core, comes from the infrared of the Earth, which is approximately 3 kilowatts. So this is obviously much smaller external heat input than the hot case, and you must also add the internal heat that's added as well. So using a total of 10 kilowatt load, 6.5 approximately from the internal, and a little bit greater than 3 kilowatts from the external, you approximate a total of 10 kilowatt load. And setting this equal to the emission from the core, and using the area that we are using for multi-layer insulation, as well as the area that's white paint, using those values, you then get the emission, and you can solve for the temperature of the core, which reaches negative 9 degrees Celsius, which is very borderline the lower range of allowable temperatures. But as we mentioned, this is with the safety margin. This is worst case scenario. So in all reality and all practicality, it wouldn't actually reach this low of temperatures. So now we'll pass it on to our final speaker, Trey Castellanos.
Alright, so now I'm going to walk through how the system performs thermally in both the hot and cold cases, and how we maintain the required core temperature range. Starting with the hot case, our radiators operate at around 315 Kelvin and are able to reject the full heat load of 16.3 kilowatts. This is the combination of the 5.5 kilowatts generated internally and the absorbed external radiation loads that flow into the thermal loop. Because our radiator surface temperature and area were sized specifically for the worst case heat rejection scenarios, the core never exceeds the 40 degrees Celsius limit. On the cold side, the situation changes dramatically. Once we enter the eclipse, there's no direct solar load and essentially no reflected albedo. So the environment's influence drops drastically. That means that the heat load falls to around 6.5 kilowatts, and as a result, our radiators cool all the way down to about 260 to about 265 Kelvin. When that happens, if we continue rejecting heat at the same rates, the core temperature could fall below our minimum allowable value of 10 degrees Celsius, negative 10 degrees Celsius. So we include two extremely common spacecraft control approaches. One of those is the radiator bypass control, which reduces the mass flow of ammonia through the radiators so that not as much heat leaves the spacecraft. The other approach is using small trim heaters, which are placed at critical locations and provide a small thermal boost to prevent overcoating. Okay, next we'll go over some of the system advantages of our satellite. So first, we are using a single closed loop ammonia system, and ammonia has excellent thermal properties for this specific application. It also has a long track record in actual aircraft and spacecraft systems. So there's a decent chance that nothing can go wrong. Like there's a very low uncertainty in how it behaves. And second, because it's a fully closed loop, there's no propellant loss. The spacecraft never loses working fluid over time, which is very crucial to a long lifetime mission. Third, our radiator area and power system were sized with margin based on our actual numbers, not idealized values. With an 18.5 square meter radiator requirement and a 22.5 square meter solar array, there's extra performance margin built in while staying mass efficient. Fourth, our battery capacity of about 20 kilowatt hours is sufficient to ride out the full 3-hour eclipse while not stressing the spacecraft too much electrically. And finally, from an operational standpoint, we have well-defined control approaches for both extremes, bypassing the hot and cold requirements. Finally, to wrap up, our required radiator rejection area is approximately 18.5 square meters, which we're implementing as 2 deployable panels, each around about 9.25 square meters. Our required solar panel area is around 22.5 square meters, which meets our 7 kilowatt electrical requirement while still supporting eclipse recovery. Our battery capacity is about 20 kilowatt hours, which is matched to the 3-hour shadow period of the orbit. Most importantly, our core temperature stays within the negative 10 to 40 degrees Celsius range under both hot and cold conditions. So, overall, our design fully meets the requirements for this project. Thank you.